about tides, we think of two things: tidal height, how far up the beach the water will come, and tidal streams, how fast the water moves whilst travelling up the beach. Tidal heights are measured as a high water, the highest up the beach the water will go, and a low water, the lowest down the beach the water will go. For this change from high water to low water to occur, the water has to move. This movement is the tidal stream, having both a direction and speed of travel. The tidal stream towards a high water is called a flood tide, whilst the tidal stream towards a low water is the ebb tide. So why does this happen? Well, the two are linked and driven by the same underlying forces. Our oceans remain on the planet because of Earth's gravity. Without this, they would float out into space like every other object that's not attached. But two other gravitational forces at work influence the total force holding water on the planet. First, the Sun, the gravitational force holding Earth in orbit and stopping us from drifting endlessly into space, and, of course, the Moon exerts its gravitational influence over the water on Earth's surface. Let's mark some positions on Earth so we can start to understand what's happening. First, we'll show Earth's gravity. Fortunately, this is always the overriding force, essentially stopping the oceans from floating into space. Next, let's overlay the impact of the Moon's gravity at each of these points. The gravitational pull at each point is towards the centre of the Moon, so wherever we are on Earth, the Moon's gravitational influence is in the same direction. On the side of Earth with the Moon, the impact is working directly against Earth's gravity, reducing the total downward pull on the water. On the opposite side of Earth, the Moon and Earth's gravitational pull are working together, increasing the entire downward force, and, of course, between the 2 points, the downward influence varies depending on the angle between Moon and Earth. This creates different amounts of downward gravitational pull at each point on Earth's surface, resulting in a bulge in the ocean. Where there is less downward force, the ocean is higher; more downward force, the ocean is lower. As the Moon orbits Earth, its position of influence changes, and the bulge follows the Moon's orbit. That would be simple if that were all there were to it, but of course it's more complicated than that. What's actually happening is both Earth and the Moon are rotating together as they orbit the Sun. These two astronomical objects, bound together by gravity, rotate around their collective centre of mass, about 1,068 miles below Earth's surface in the direction of the Moon. Spinning on this offset centre creates centrifugal force, throwing the water off the planet. While the force exists on both sides, it's strongest at the point opposite the Moon, causing the ocean to bulge outwards almost directly opposite the Moon's gravitational bulge. The net effect of this is the creation of two bulges of water roughly in line with one another. These two bulges of water are orbiting the Sun, which exerts its own influence over our oceans in the same way as the Moon. However, its impact is about a third. This is because, whilst a much larger mass, as Newton's law suggests, gravity decreases with distance. It's these bulges that create our high and low tides. The bulges are the high water and the midpoints are the low water. Earth is essentially rotating inside this bowl of water, which creates the high and low waters we experience. If we look at a view of the North Pole, and mark the UK on the globe, it passes under 2 high and 2 low waters in every rotation. The tide floods as we approach the deeper high water and ebbs as we come to the low water. Of course, the Moon's position in relation to Earth is constantly changing. As Earth rotates through its 24-hour day, the Moon is progressing its 27.3-day journey around Earth. In 24 hours, the Moon has gained just over 51 minutes from any specific point on Earth, pushing forward each high and low water on average by 13 minutes in a dual high-low water location. Hang on, dual high-low water location. So that must mean some places don't have 2 high and 2 low waters a day. Let's take a look at Earth with a view of the equator. First, the Earth's axis is tilted towards the Sun, so the ecliptic plane is not in line with the equator. Second, the Moon's orbit around Earth is also not on the equator. It's about 5 degrees offset from the ecliptic plane, so the bulges of water move north and south as the cycle unfolds. We can see these orbiting systems are not on the same plane. This means that some places on Earth will only experience 1 low and 1 high water as they rotate under the ocean. This tidal sequence is known as diurnal, 1 high and 1 low tide every lunar day. Semi-diurnal areas are most common and experience 2 high and 2 low tides of approximately equal size every lunar day. Finally, a mixed semi-diurnal tidal area experiences 2 highs and 2 low waters of a different size every lunar day. There are a few single tide areas. About a third of the world experiences mixed tides, whilst the majority experiences 2 tidal sequences in a single day. When we put everything together, we start to see a rhythm. The Sun plays its part in the cycle, however, as Earth orbits the Sun, it remains a constant force. If we introduce the Moon, we can start to understand the 4 key positions this creates for our tide. First, we have a new moon. This is when the Moon and Sun are approximately aligned on the same side of Earth, resulting in their gravitational and centrifugal influences being in line. This forms more prominent bulges on either side of the planet, stretching the water and creating very shallow areas between them. The tidal range, the difference between the high water bulge and the low water flat, is most significant at this point of the astronomical lineup. This is when we experience the highest and lowest tides. As the Moon starts its lunar orbit, it progresses to the first quarter. The tidal range gets progressively smaller as the forces begin to work against one another until they work as far apart as astronomically possible, creating a much smaller bulge. The first quarter is when we experience the least difference between high and low water, the smallest tidal range. As it continues the journey, this time with the Moon and the Sun on either side of Earth, the tidal range grows again until eventually it peaks at the third key stage of the cycle. This is when we experience a full moon. The Moon continues its journey towards the last quarter, when again the astronomically contradicting alignment flattens the bowl of water and the tidal range bottoms out. The Moon then enters the last part of its cycle, moving from the last quarter back to a new moon with the tidal range once again progressively increasing. And so the cycle continues. Whilst the 4 key lunar phases remain, The pattern in the relationship between Sun, Earth and the Moon is made more complicated by their elliptical orbit of the Sun, Earth rocking back and forth on its axis, and the 5-degree angle of the Moon's orbit around Earth. With the Moon orbiting Earth approximately every 27 days, and Earth and the Moon orbiting the Sun roughly every 365 days, there are 18.6 years worth of variations in the relationship between these three astronomical bodies. 18.6 years of different tidal conditions, known as the tidal epoch. So how does this play out for us in our experience of the tides? If only water covered Earth and there was no landmass, two shallow waves would move around the planet following the Moon's orbit. Earth would rotate underneath them, creating a simple uniform high and low water pattern with a constant flow of water or tidal stream. This natural astronomical influence alone would create an approximately 60 centimetre difference in the height between the highest point of the bulge and the lowest. But of course the land interferes with this simple model. Let's look at Earth from the South Pole, south of all the major capes. Here we find the only unimpeded path around the planet. Everywhere else on Earth the bulges cannot flow interrupted. Instead, landmass impacts the movement of water. As the land gets pushed through the bulge, other than going over it, where it can't, it gets deflected. So the water has to move around it. In fact, most of the tide we experience is a harmonic originating from where the bulges can't flow, modified, amplified and reflected by the landmass. This affects the height of the water, its speed and its direction of flow. In other words, everything we would consider to be tides. Further away from the coastline, less amplification and deflection occurs. So the middle of the oceans is subject to very little astronomical influence. Here, the currents are mainly driven by natural occurring forces on Earth. There are surface currents and deep ocean currents at work. Surface currents are driven by the wind. As the wind blows over the surface, the friction creates waves moving the top layer of water. In turn, this drags along the layers below and so on and so forth. This frictional effect of the wind can influence water movement up to 400 meters deep. Below that, deep ocean currents are natural flows of water around the Earth, driven by water temperature, density and salinity, the amount of salt in the water. They form part of nature's redistribution system and are fundamentally part of the environment we experience. This is known as the global conveyor belt. As we move back towards the coastline, the landscape and topology become the overriding influence on our tides. These coastal tides impact most of our time on the water. Then, of course, there's the famously non-tidal region, the Mediterranean. How does that work? In effect, it's like a bucket of water sitting on the planet with a tiny hole at the top, opening to the rest of the oceans. It operates in isolation from the rest of the water on Earth, effectively having its own astronomical tidal system. There are tides, however the average range is 30 centimetres, so they generally do not impact us. As the bucket is moving at a constant speed, there's also no flow of water to speak of. This is essentially true of all bowls of water on Earth, such as lakes or lochs. Let's look at how all this plays out for us on the water. Around the time of a new or full moon, we experience the peak tidal range in the cycle. This is a spring tide. In the UK, this will result in 2 large tides in just over 24 hours. Roll forward approximately 7 days, and around the time of the first or last quarter, we experience the smallest tidal range in the cycle. This is the neap tide. Again, in the UK, this will result in 2 small tides over a 24-hour period. Whilst these spring and neap tides exist in the cycle, they're not the same range every time. Their significance is that they mark the turning point of each phase, when the cycle changes from an increasing range to a decreasing range, the spring tide, or a decreasing range back to an increasing range, the neap tide. The high and low water slowly decreases from a spring to a neap tide and increases when moving from a neap to a spring tide. Following the Moon's approximate 28-day cycle around Earth, there is an alternate spring and neap tide roughly every week. Over the course of the tidal epoch, the complete 18.6-year cycle, the spring tide will experience its highest point, mathematically the highest the water will ever rise. This is highest astronomical tide, or HAT. The opposite of this is lowest astronomical tide, LAT. Theoretically, the lowest the tide will ever fall. Whilst an infrequent event, this is essentially worst-case scenario. Most chart publishers use this calculated value as their baseline, or chart datum. Due to landscape and topology, these cycles play out significantly differently depending on where we are in the world. Differences in the average range, the amount the water will rise and fall between a high and a low water, and of course with that, differences in the speed the water will flow. As we saw, the Mediterranean has a minimal tidal range with an average of just 30 centimetres. Port Fraser, one of the RYA training ports, can experience a range of 4.6 metres, about the height of a double-decker bus. This is comparable to somewhere like Southampton in the UK, where the range can be 5 metres. Victoria and Dawson Harbour, 2 more fictitious RYA ports, have tidal ranges of 6.3 and 8.4 metres, nearly 2 double-decker buses. Places such as the Channel Islands, Guernsey, Jersey and Alderney regularly experience ranges of 10 plus metres. But the second biggest tidal range in the world is the Bristol Channel, with the water regularly rising and falling by more than 3 double-decker buses, leaving the champion of tides with a range often touching 4 double-decker buses or nearly 17 metres is the Bay of Fundy, Nova Scotia in Canada. So how do we work out what the tides are doing and how they might affect us? Well, first we need to know the calculation for the Moon's gravitational influence, and then the calculation for the centrifugal. Only joking. Fortunately, the hard work and calculations have been done for us. The pre-calculated data is compiled using both astronomical calculations and historical information, which means it considers local anomalies that will impact the tide. So all we have to do is learn how to look up the relevant information and use the tools provided. The Almanac is one of our key sources of tide data, including tools to work out height of tides and tidal streams. Tide info is also provided on many charts, again, both the heights and the streams. Of course, in this day and age, there are many electronic sources too to help us understand and work out tidal info. We can also answer some tide questions whilst out on the water. Tools such as tide gauges, often found in harbours, and even our own depth gauge provide a quick, easy way to understand the current state of tide. Now we understand what causes our tides, In the rest of this module, we'll learn how to use all the tools available to us to work out the impact it will have on our time on the water.